Hello and welcome to this webinar session on Explicit Dynamics Analysis with SIMULIAWORKS. My name is Sashi Sitambaram and I'm a Simulation Technical Manager and I'll be your presenter today. At the end of this webinar, I will be sharing my email address, so if you have any questions on today's content, please feel free to send that to me directly. So let's start off by answering the question, what is explicit dynamics? And let's first define what a dynamics analysis is. It basically is problems involving inertia effects. So any type of crash testing, impact testing, drop tests, these will all be considered dynamic problems. When it comes to dynamic problems, there's two ways to approach or to solve it. One is using an implicit method and the other would be using an explicit method. The explicit dynamics procedure is often complementary to the implicit solver. So when you think about whether or not you should use an implicit solver and an explicit solver, it's not so much that it is two different types of solvers, it's more so two different methods to solve the same problem. Implicit dynamics do not place an inherent limitation on time increment size. So when you use an implicit method, you would typically set a starting time increment. And if the time increment is not fixed, it is set to automatic. That time increment can change depending on how the step is solving and converging. Every step is solving and converging. And with an implicit method, that is a requirement that every step has to solve and converge. Now, that's really not the case with an explicit dynamics. An explicit dynamics analysis does not have to necessarily solve and converge for every step, but every step has a much shorter time increment. And the type and duration of loading is independent of the time increment. Now, there's many different reasons why someone should pick an implicit over an explicit or an explicit over an implicit analysis to solve a dynamic problem. But one fundamental rule of thumb that I've used over the years successfully is how the system, how fast the load is being applied onto the system in real world. So typically, if you have a slow moving load of 1 second or more, then an implicit dynamics analysis would probably work fine. If you have fast moving loads, which are less than 1 second, then you would probably need to use an explicit dynamics analysis. Now, there's many other reasons why explicit dynamics is the better choice, and I will be going through a few real-world examples where explicit dynamics was used and why explicit dynamics was chosen. Now, there's a lot of literature on explicit dynamics online. So if you go and Google, you can Google explicit dynamics analysis. You will really learn the mathematical formulas behind explicit dynamics. How does it differ from implicit dynamics? And some of the tools that come with explicit dynamics that make it a better option and actually solves analysis quicker than implicit dynamics in certain type of analysis. So within SIMULIAWORKS, we have both implicit and explicit solvers, and there are two roles within SIMULIAWORKS that allows you to solve dynamics analysis. First is structural performance engineer, which only comes with an implicit solver. And the second role is a structural mechanics engineer, which has both implicit and explicit solvers. As part of the structural performance engineer, you'll be able to solve many different types of analysis. So linear, nonlinear static, linear dynamics, low frequency nonlinear dynamics, nonlinear heat transfer, thermal stress, structural acoustics. With structural mechanics engineer, you will get everything that comes as part of structural performance engineer. And with the addition of the explicit solver, you'll be able to do a high-speed dynamics, so any type of drop test or crash analyses, large nonlinear quasi-static analysis, so you'll be able to simulate deep drawing and blow molding. And any problems or any solutions that have discontinuities, such as impact, wrinkling, and cracking, would need to be solved using an explicit solver. So let's take a look at how to set up an explicit analysis, and we're going to do that by simulating a soda can being crushed under a hydraulic press. So the simulation will end up looking something like this. And while this is a simple example, really don't need to simulate this in real world. This type of deformation can be applied in many applications. The type of material being used here is common to is similar to sheet metal components. So any type of crash test body, automotive body being crushed, things like that, has the same setup as an application like this. So let's go ahead and switch over to the 3D Experience platform. And to import your 3D model, you can actually just go up here and select on Import. And the 3D Experience platform actually allows you to import many different file formats. So 3D XML files, STEP, IGES, all different types of SolidWorks files, assembly end parts. You can import using import it directly. So I have already imported the model in. So you can see right here. So this was imported in as a 3D XML file. So not only it brought in the 3 components, it also brought in some material information. And the reason why I'm bringing that up is because material is pretty important here for this can. We need to have appropriate nonlinear material conditions to ensure that we get the right deformation for this can. For these 2 plates, so this is just a base plate where the can is sitting on. And this plate on the top is actually what's going to crush the can. These 2 are just rigid bodies. So I'm not too concerned about the material condition as long as it has a property which makes it stronger than aluminum. We're good to go. So I don't really see any deformation or stress on these 2 components. So for the aluminum, we can actually just take a quick look at the material properties here. And we can see here under mechanical, we have damping for the mass proportional damping. We have some elastic conditions, and we also have some plasticity information to ensure the nonlinear deformation of this can. I can close this out. So to start off setting up this analysis, we first have to mesh these 3 components. So taking a look at the can, so I'm going to just hide these plates, and to do that I can just hover over it and hit F7 on my keyboard. So if you zoom in, we can see that this can actually has a very, very thin wall thickness. So typically if you have a component like this, sheet metal component, you want to use a shell mesh. And there's a few different ways we can approach that in SIMULIAWORKS. But for this specific geometry, I'm actually going to use a method where I'm going to extract the surfaces. And then when I assign the thickness, I'm actually going to just reference the solid model. And the reason why I'm doing that is because this can has a non-uniform thickness because of the top and bottom lip. So this lip right here is thicker than the rest of the can. So is the lip in the bottom. So, and you'll see how I approach that. So to extract these surfaces, I'm actually going to go into my model prep app, which is right here. So I'll select on model prep. And this is asking me to link it to the shape that I'm working on, which is the can. So I'll select on the can. And I'm going to go into my Idealize tab right here. I'll select on Extract, where I can extract the surfaces. And for propagation, I'm going to just select a tangent propagation. So this essentially will help me select all the tangent faces. So when I select one face, it will just continue selecting faces until it comes to a tangent discontinuity. And then at that point, I can just manually select the other faces. So here I have two other faces to select. So this face and this face. And close this out, and I can just say OK. And now we can see that we actually have those three surfaces here. Now, I actually need these three surfaces to be a single surface. So I need to join them together, because when I create my shell mesh, I can only select one surface. So to do that, I can go into my check and repair tab and select on join. So I can actually just select on these three extract surfaces and say OK. And now I have that single surface to work with. So now I can actually exit my model prep app. And I am going to go into, so now I'm ready to mesh these three components. So let's go ahead and just start with the can itself. So I'm going to switch over into my mesh app. And for the can, I'm going to just use a surface quad mesh. And I'll select the surface. I'm actually going to hide the body just so that I don't accidentally select it. So you can see that now this body is hidden. When I zoom in, there's no thickness to that can. So I know for sure that the surface was selected. I want to make sure that the mesh is going to be properly fit within all my edges. So for the geometry, I'm going to actually make the angle between surfaces and angle between curves to 0. And I'll say OK. And I'll hit mesh. So we can actually see how this can looks. It's has a nice dense mesh. So this should give us quite a pretty good results. So I have two other components, the top and bottom plate, that I need to mesh. So to bring back those components, I just have to hit F8. Like I said earlier, these two components are rigid bodies, so I'm not too concerned about creating a super dense mesh here. So I'm actually just going to use a sweep 3D mesh, which is the easiest way to mesh components like this, where when you select one face, it automatically selects the other face and it will just mesh across that thickness. And for here, I'm just going to use a 15 millimeter and one layer. And I'm going to hit mesh. You can see how that mesh looks. Say OK. And I'm going to do the same for the top plate. It's like that, mesh. OK. So we're good to go. So now the components are meshed. I can actually hide the mesh. And to do that, I can just right click this right here with the mesh icon and say hide. So now all I see is just the geometry, the original geometry. So now I need to actually assign a thickness to my mesh that I created to the surface. And to do that, I'm going to go into my model app, which is right here. Under properties, I have my shell section. I'm going to select on that. And I'm going to select that shell, the surface. And for the thickness, we can see here that we do have an option to just put in a number. But like I mentioned earlier, this component has a non-uniform thickness. So instead of actually putting in a number, what I'm going to do is I'm actually going to define the thickness from the solid. So I'm going to say from solid, and it says get thickness from, and I can just select that solid body. And you can see it automatically brought in that material information from the solid body and say OK. And now this surface has a thickness to, for the calculation, for the mathematical calculation. And it also has a material assigned to it, all of it extracted from the solid body. So it's very easy to do. Now, if you want to make sure that this surface has a thickness to it, you can actually go into our model plots right here. And I just need to update the model so that I can create the proper plots. So it's just updating the model. and I'm going to select on contour plots. None, layer thickness, that's good. For this, I'm going to do element faces. For this, I'll do a mesh outline, and I'll say apply. And okay, so now we can actually see the thickness of this can. And like I had mentioned earlier, there is a difference of thickness for the top and bottom lips versus the middle of the can. So now that we know for sure there is a thickness to the shell, now we can continue on setting up this analysis. So to hide this this visualization, I can actually just come in here under my plot, this layer thickness plot. I can just right click this and just deactivate the plot. Okay. So now I'm going to go back into my scenario app, which is where I can set up my analyses. So this analysis is going to be an explicit dynamic. So you can actually see here those two types of analysis. The implicit and explicit are right here. So I'm going to pick on explicit. And for my time step, I'm going to be using 0.04 seconds. And the increment type is automatic. And I'm going to say OK. So now it has an explicit dynamics analysis step procedure. The next thing I'm going to do is I'm actually going to assign what we call mass scaling to this component. Now, to do that, it actually resides right within the explicit dynamics procedure. If I hit this arrow, mass scaling comes up. Now, mass scaling, you can apply mass scaling essentially to scale the mass of the entire model or to scale the masses of individual elements in an explicit dynamics step. And it does this without modifying the underlying material definition. When used appropriately, mass scaling can often improve computational efficiency. So this is essentially, in other words, when the non-physical mass is added, which inherently increases the density, which then increases the stable time step, it reduces the total solution runtime of the analysis. So, and if you take a look at how we set this up, you'll get a better understanding of this. So for here, I'm just going to say whole model. I'm going to say throughout the step and below minimum. And for this, I'm going to say, type in this target time increment. So if the time increment goes below this number, which is very, very small, it will add non-physical mass to bring the time increment up to this number. So this is a great way to ensure that I'm not it's not going to use an super duper small time increment, which then increases the solve time. And the frequency here, I'm just going to use 500. But just be careful when using mass scaling because if it's used incorrectly, it can affect the results. So in cases like this, this time increment is so small. If it comes all the way down to this time increment, there's very few elements that it will actually affect. So it won't really affect my final result. So I'm going to say OK here. So now the next step to my analysis is to add the load, the applied translation onto this top face. Now to do that, so before I add the applied translation, I'm just kind of thinking forward here. I don't want to apply it to the entire face here because, again, this is a rigid body. So a really good way to add the applied translation without overly imposing physical constraints to this plate, we can do this by adding what we call a coupling. So to add a coupling, I'm actually going to go back into my model app. and I'm going to go into my connections, and I have coupling right here. And if I select this face, so when you select two faces, it will essentially create so when you select two supports, the simulation couples the faces or edges to a reference point located to the centroid of those two faces or edges. So if you select one, it will just do a centroid of that single face. So here, what I'm going to do is I'm going to do a coupling type is kinematic, and say update mesh, and say OK. So now I have that coupling right there. And going back into my scenario app, before adding the before adding the translation, I do want to add an amplitude of how that translation is going to apply, because I'm not going to apply a direct translation to the part. So I'm going to actually go into my setup tab right here, and right here I'm going to say a smooth set amplitude of how that that translation is going to be added on. So I'm going to go from 0 time with 0 amplitude, and then 0.04 time to the full translation. I'm going to say OK. So now we can actually go into the interaction. Sorry, the load, and apply the translation. So I'm going to select on apply translation. And for the support, like I said, as opposed to selecting that entire face, I'm just going to come in here, select in connections, and I have my coupling. I'll say OK. And you can see that how it applies the translation on one point, but it actually ties in all the edges. So it basically ties in this entire component together. The direction is going to be a Y direction, and it's going to be negative 100 millimeters because I want it going down. And I'm going to just use the global axes. And for my amplitude, I already set up my amplitude before. You can see that now it's in my drop-down menu here. So I'm going to do the smooth set amplitude 1, which is what I just set. And I'm going to say OK. All right. So now I also want to restrain this bottom plate. So to do that, I'm going to go into restrain, and I'll select clamp and select this face, say OK, easy as that. So for this top face, I want this top face to only travel in the Y direction that it's translating in. So I would also want to do a fixed displacement. So again, I'll select that coupling. I'll say OK. And I'm going to lock the translation in the X, Z, and also lock all the rotation, so it will not rotate. So I'll say OK. So now this plate can only travel in the direction of its translation. All right. So I have my restraints. I have my loads. The next thing I need to do is set up my contact condition here. So I do have a friction coefficient I need to set up. So I'm going to go into interaction, and I'll select on contact property. So I will check my tangential behavior right here, where I can add my friction coefficient 0.2, and I'll say OK. And I'll come into my general contact condition. So as you know, or may not know, that with SIMULIAWORKS, all contact condition is considered independent and no penetration by default because of its superior contact conditions. But you just need to specify your general contact, especially if you have any friction. So what I'll do here is for my global contact property, I'm going to just reference that friction contact property that I just set up, that contact property 1. And I'll say OK, and that's it. So now my general contact is going to be driven off my contact property, which has a friction of 0.2, a friction coefficient of 0.2. All right, so that's about it. That's the entire simulation setup. The last thing I need to do here is to set up my output conditions. So I'm going to go into my Simulate tab and select on, by default, you would already have an output set up. So I'm actually just going to double click my output 1, and I can actually change my number of intervals here to, I'm going to change it to 40. So it actually collects more information. So just so you know, this output is how the result is being collected. So if I have 40, it's actually going to collect 2 times more information than what I had before. And you can also specify what type of information you would like to collect as it's solving. So I'm collecting all my different stresses, strains, displacement information, all that. It's right here. So I think I'm actually good here with the output. I'm going to hit OK. So at this point, I can actually just hit my simulate, and the simulation will run and solve. So I've actually already pre-ran the analysis. All right, so let's switch over to this tab right here, which has the completed analysis. So you can actually see here the results are already loaded up. So to view the results, once you run the analysis, you will get results for every step. And you can see here that I have many different plots. So I can actually pick my deformation plot. And it's actually, you can actually see the animation of how the can is deforming. We can take a look at my displacement plot. So this will give you some displacement values. And if you take a look at my plastic strain, you can take a look at that as well. So to have a better view of how the can is deforming, there's a few ways we can approach that. So I'm actually going to go into this plot right here, and I can actually say apply transparency and say OK. And you can actually see right through the model. And you can also do an animation, and you can see how it deforms from the top. So another way to approach this, I'm actually going to change back the transparency. Pause this. And I'm going to change this to display group. And under entities, I'm going to remove the top plate and bottom plate. Close. So now all that's left is the can. So this is a clear view. And if I hit animation, you can see clearly how that can deforms. All right, so let's go back to the PowerPoint. And if you take a look at the results, you can see as the can is deforming under the hydraulic press, the results are almost identical. And as we see for total compression, again, very identical results. So, the explicit solver here does a really good job solving the analysis and providing some very good results. So let's take a look at some real-world examples of where explicit dynamics analysis can be used. So this is a rubber bumper installed on railway platforms. So the reason why, and you can actually see the comparison to the physical testing. Again, very, very, very close results. And the reason why explicit dynamics was used here is because of large deformation, complex context, and dynamic impact. So quick, fast, it was fast loading. Wire crimping. So, this type of analysis has extensive and complicated context conditions. So, it will typically require very short time increments. So, when you have a lot of complex contact and short time increment, that also is probably a very good sign to use an explicit solver. So here's another example, which is a rail car aluminum crash module, this piece right here. So you can see the difference between the physical results versus the simulated results. Very, very similar. The reason why Explicit Dynamics was chosen here is because of the elastic plastic behavior of the metal, progressive damage and failure of the welding, large deformation and frictional contact. Here's another example of metal forming. So as you know, and this has been mentioned many times, SIMULIAWORKS uses the Abaqus solver. So this was actually done directly on Abaqus Explicit. But if you would run this analysis on SIMULIAWORKS, you'll get the exact results, identical results, being that it uses the same solver. So this was done for Coca-Cola. And here's another example where this is the wiper blade rubber piece, which actually is the one that is contact to the windshield and wipes away the rainwater. So this problem could have been done using an implicit solver or an explicit solver, but the implicit solver will not proceed past the dynamic transition point without employing special stabilization techniques. So as opposed to having to deal with that, we could just easily solve this problem using the explicit solver. So as I had mentioned before, a lot of these problems you can use both methods, but the explicit solver gives you tools like the mass scaling and the way it solves time increments that it's able to easily solve these problems. So what are the advantages of Explicit Dynamics? To summarize, it is designed to solve highly discontinuous, high-speed dynamic problems efficiently. It often provides a more efficient solution for very large problems. And it contains many capabilities that make it easy to simulate quasi-static problems. So to learn more about SIMULIAWORKS, what you saw today with the Explicit Dynamics, to learn about what you can do with the Implicit Dynamics, and to learn about SIMULIAWORKS in general, you can go to www.solworks.com/SIMULIAWORKS. You can also go onto my.solworks.com and search Simulia Structural to view videos, blog posts, and just a ton of information on SIMULIAWORKS. You can also reach out to your SolidWorks VAR. All your SolidWorks VARs have access to SIMULIAWORKS, so you can actually see all these different types of analyses, and you can request a demo. You can even try to get you can even try out the software yourself. Just reach out to your VARs to do that. And as promised, this is my email address. It is sashi.sitambaram@3ds.com. So if you have any questions on today's content, please shoot me an email, and I look forward to hearing from you. Thank you all for joining me today, and see you next time.